Sketches capture the essence of visual entities, allowing humans to communicate abstract visual ideas. An animated sketch opens another dimension to the expression of these ideas. In this paper, we propose a method to breathe life into a static sketch by generating semantically meaningful short videos from it. In terms of existing methods, the immediate candidates for this task are image-to-video pipelines, but even the best closed-source models struggle with this type of input. They are strongly biased towards real data, so at best we get the sketch to change shape or transform into a real object. On the other hand, sketch animation methods are almost always based on direct reference motions and mapping them to user-annotated key points. This can be fine for humanoid figures, but really breaks apart when you're trying to animate, say, a fish. So in this context, we define 3 goals for our method. We want our sketch to be animated according to some prompt that describes reasonable motion for the subject. We want this motion to appear natural and smooth, and we want to preserve the sketch identity. So how do we achieve these? We represent our sketch as a set of strokes, each which is parameterized by 4 control points. Our goal is to learn per frame offsets for these points, representing the desired motion. We begin by duplicating the input sketch k times for each of our k frames. Then, we simply concatenate the parameters and feed them into a network M that learns to predict the desired offsets, which are then summed with the input points to form the SVG. To train our network M, we utilize the prior knowledge of pre-trained text-to-video models. The points Z are fed into a differentiable rasterizer, diffvg, that renders each of the frames so that we now have our video F in pixel space. We then incorporate the SDS loss to guide the training of our network. This loss allows us to use a pre-trained text-to-video diffusion model to estimate the gradients that will optimize our parametric model to output results that better align with the text prompt. Now, the pipeline gives results that look like these. The sketches are moving in a way that fits the subject and the prompt. However, we've got big shape changes and a lot of temporal noise in our sketch. We've identified 2 main issues causing this. First, the SDS loss can be minimized by changing the subject shape. And second, large changes, such as translation, require large displacements. So we address this by integrating this understanding into our network design. The key idea is to separate the network into 2 branches. The first is the local branch. It's completely unconstrained and can be used to create the local motions. The second branch is the global branch, which is responsible for larger global changes like rotation, scale, or translations across the frame. We constrain it by getting it to predict parameters for 1 affine transformation metrics for each video frame. This way, it can introduce larger movement without causing the shape to break apart. Now, with this architecture, we have motion, which is much smoother and cleaner, and we've got better shape preservation. So let's see some results. The biggest advantage of our approach is the high level of generalization. It works on many different subjects and classes, from animals to human motion to objects. Our animations are also given in SVG format, which means one can easily edit the results as a post-process by changing the stroke style, for example.